Why does the discrete metric generate the discrete topology? Well, let's say we're working with the set X. So we have this set. Okay, what's the discrete metric on X? The discrete metric is dx comma y equals 0 if x equals y, and 1 if x does not equal y. All right, and x and y are points in X. So what's the discrete topology? The discrete topology is just the power set on X, which is just every possible subset of X. So this would be X, any singleton, and then it's just any pair, and so on. And then it also includes the empty set and X itself, because those are subsets of X. So it's every possible subset of X. So what does it mean for a metric to generate a topology? Well, it just means that every subset of X that is open in the metric sense with respect to this metric, that subset would also be open in the topology in question, in this case, the discrete topology. So, for example, we'd want to show that every subset open in the discrete metric sense is also in the discrete topology. So, being open in the metric sense means that for some subset y of X, so for some y of X, y contains an open ball around each of its points. So for every y in big Y, there exists, I think this is the there exists symbol, some ball around Y, which is a subset of Y. So let's look at a specific subset of X. So let's just say that we just have this singleton set lambda. That's all that's in the subset, and it is a subset of X. Okay, so is it open in the discrete metric sense? Well, so to answer this question, we need to see if we can find a ball around lambda. And can we do that? So first things first, every point in X that is not lambda will give you a distance of 1 away from lambda. So having observed that, if we pick any r, which is greater than 0 but less than or equal to 1, then the ball around lambda with radius r is only going to have lambda in it, right? Because there's no point closer than a distance of 1 to lambda. And then the distance of lambda to itself is 0. So of course it would be in the ball. Now, the singleton set is clearly a subset of itself. So because of this, the singleton set lambda contains an open ball around all of its points. So this is open. It's open in the discrete sense, and we already know that this set is in the discrete topology. So therefore, we have kind of discovered that this set is open in the discrete metric sense. Therefore, this part of the discrete metric will generate the singleton sets in the discrete topology. So we can use the same logic for pretty much any set in the discrete topology. So let's say we have this set, which is just lambda, alpha, and delta. Well, like we did before, every possible distance from every point is 1, unless it's the same point. So the distance between lambda and alpha is 1, and so on. So we can pretty much do the same thing we did with the singleton sets, but for each point here. So we can find a ball around lambda, So as long as R is less than 1, and we can find a ball around lambda, which again is just lambda, like we did before. Same thing with all the other ones. And so on. And these are all subsets of lambda, alpha, and delta. Now because of this set contains an open ball around each of its points and is therefore open in the discrete metric sense. So you can pretty much continue this logic for every possible subset of X. And because you can do that for every possible subset of X, remember that the definition of the discrete topology is every possible subset of X. So because you can find a way, you can find an open ball for every possible point in each of these subsets, then they're all open in the discrete metric sense. Therefore, the discrete metric generates the discrete topology.